Now we're also looking at a couple of other quantization techniques. Scalar quantization is another one where you simply take the 32-bit vector and you reduce it down to 8 bits. So there's a lot of different things that people are trying out. But the reason why this reduces cost, the reason why I said people are not using it as much as they should is that it's almost like a superpower, right? You start to think that using vector databases will cost you thousands of dollars, and then you apply quantization, and not only does it cut down the memory cost, but you can also run, depending on how many objects you have, you can run brute force search, right? If you've got 10,000 objects or 50,000 objects, you use binary quantization, you can run in-memory search. You don't need to build approximate nearest neighbors indexes or anything like that. So this is another feature that we implemented where given a certain number of objects, you can just vectorize them, then we binary quantize them, and then we do we call it flat indexing, where we don't even build up the HNSW graph. We just do brute force comparisons. And because the binary vectors, you can optimize the distance comparison between them. It's quite efficient, and you can get away with just brute force searching through them up to a certain number of objects.
Hey buddy, welcome back to another episode of How AI is Built. Today we have a very special guest. Zain Hassan is an ML engineer at Weaviate working on vector databases. We will cover quantization, hybrid search, multi-vector strategies, and more. If you're struggling in reducing cost or improving the performance of your vector database, this is the conversation for you.
My background is in engineering, but in graduate school, I was focusing on machine learning and data science. This was back in 2015. And then after graduate school, I went in and I started working as a data scientist. And then I saw this new opportunity of a vector database. Back then, the company wasn't called Weaviate. It was a different name. Weaviate was a product that the company was making. I applied and I got a position. And at that point, I didn't know what a vector database was. This was like 2 years ago. Vector databases were very, very new before ChatGPT. And then I started learning that vector databases are not too different from just representation learning in machine learning, which is quite old, using like autoencoders to embed different data types into latent space. And then you would have like 1,000 dimensional representation. That's basically what the vector in a vector database is. And then since then, I've been learning more about the database component of these things. So how do you do this really quickly? How do you make sure that the accuracy of the retrieval that you're doing with these vectors is as high as possible? So all of these kind of little nuances that have to do with scaling up basic representation learning to handle in production workloads. That's what I've mainly been learning about.
What do you think is like an underappreciated or unknown thing most people don't really think about for vector
Yeah, I
databases?
think there's a couple of things. First of all, when people think about vector databases, they think about them with regards to ChatGPT. So they think, oh, vector databases are a way to store my text data and then chunk it and then retrieve relevant and then give it to relevant pieces and give it to ChatGPT. But vector databases can handle text, image, audio, video data just as well. If you have a machine learning model that can encode that data, then a vector database doesn't care because the vector of an image is pretty much the same as the vector of a text. All of the mathematical computations for that vector will be the same. So going from text to multimedia in vector databases is really simple if you have a machine learning model, which there are a lot of open source ones. And then the second thing I think is quantization. So a lot of people think that vector databases are this really expensive thing. You know, it's like this fine dining cuisine. You go to a restaurant, you have to pay like $1,000 a pop or something like that. A lot of people have this view in the field that, oh, you're doing vector search, it must cost a lot. I don't think a lot of people are using vector quantization. If you're using the entire vector that comes out of the model, that can end up costing a lot. But oftentimes you don't need the entire thing. You can quantize it, and we can talk about this, and you can cut down your costs by 80% just by quantizing, depending on how much accuracy you want, right? So there's a lot of kind of tuning of costs, speed, memory footprint that I don't think a lot of people are utilizing right now. It's still a new field, but I think those are the couple of things that a lot of people are surprised to hear.
I think that's also like the two most interesting developments for me, especially in vector databases in 2024, like multi-vector support, like multi-vector for the same text data, but also multi-vector for real multimodality, and also the quantization part, like especially with mixed bread, which brought out a few really interesting models. Gonna be an interesting year. What do you think, like quantization wise? What are the trade-offs you're actually doing? Like, do you have like a matrix you're looking at or a different set of
Yeah. So
metrics?
basically, when you're evaluating or looking at how good the vector search component of your RAG stack is, there's like two or three things that you're really looking at. You're looking at how fast this thing is. So how many queries can you serve? So you can think of that as throughput. Another thing that you're thinking about is what is the total memory footprint of your index, right? So if I've got a million objects that are in my vector database, how much in memory cost does that amount to? And then you're also looking at the recall, right? So if you're passing in a query, are you even getting back relevant things? And so usually those three things you're balancing. If you have an application where recall is the most important thing, then you might want to sacrifice latency and memory consumption to boost up recall to the highest possible. So there's a lot of things that allow you to kind of fine tune and balance between those three things. Vector quantization is one thing, right? So vector quantization basically says, let's say you have a 1,000 dimensional vector. Every single dimension of that vector is currently in Weaviate is a 32-bit floating point number, right? So every dimension is 4 bytes. And so if you have 1,000 dimensions, that's 4,000 bytes per vector that's stored. And then that scales up. If you have a million, then you've got a lot of in-memory requirements, right? Vector quantization basically says, are you willing to let go of some of those bits in order to reduce the memory footprint? And so now if you can go from 4 bytes to 4 bits or 4 bytes to 1 bit, then you can basically gotten rid of, there's a whole spectrum of information that you can get rid of, and you're reducing memory footprint, but at the cost of recall, right? Because now your vectors are becoming fuzzy. You don't know where they exactly are. You're using less memory to capture the location of every vector. And so there's people have found different techniques where what is the right amount of information to get rid of, how to get rid of it, what does your distribution of the data need to look like before you apply vector quantization so that it still works afterwards. So there's a whole kind of school of methods, product quantization, binary quantization, all of these different methods that people are now working with. So you mentioned mixed bread. Cohere was also working on this. I think binary quantization is something that people are really excited about now because it's kind of amazing to think that you could have a 1,000 dimensional vector and then you could only keep 1 bit per dimension. So it's almost like saying, let's say there was a party and you describe to me the location of that party. You give me the total address. And now you tell me, now I'm not going to give you the total address. I'm just going to tell you every time you come to a street, whether you go left or right. And that's all I'm going to tell you. I'm just going to tell you consecutively one after the other, left, left, right, right, left, right, left, right. And you could do this and you could still capture vector distances pretty accurately, which is pretty amazing. So I think people are correctly excited about binary quantization.
What are the other levers you could pull to basically move along the different metrics you just
Yeah,
mentioned?
so think about a full vector is 32 bits per dimension. So you've got all of that accuracy to capture exactly how far along to move of the axis of a dimension. So if you have a 2D vector, you've got 32 bits to represent how far along the x-axis and how far along the y-axis to move. So you can exactly locate yourself in a 2D space, like a Cartesian coordinate system. You can exactly locate the vector there. If you binarize that vector, now you've only got a 0 or a 1 for both dimensions. So now you're either in the first quadrant, or you're basically in one of four quadrants, and every vector has to be in one of four quadrants. So this is the problem with binary quantization. If you reduce the number of dimensions, it doesn't work. But for 1,000 dimensions, it works really well because you can have 1,000 squared possible number of different unique vectors, and that exponential blows up much faster than the total number of vectors that a lot of people have. So this is why binary quantization is working quite well. If you find that binary quantization doesn't work, or maybe your distribution of the data is not good, right? Because what you do in binary quantization is you just say, is the dimension positive or negative? If it's positive, you turn it into a 1 bit. If it's negative, you turn it into a 0 bit. If the data is not normally distributed, let's say you don't have an equal distribution between negatives and positives, everything is a positive, then all of the vectors will just be ones. So then binary quantization doesn't work. So you have to be careful about the distribution of your data before you apply binary quantization. If you're finding binary quantization is not working, then in Weaviate, we've implemented a lot of different quantization techniques. So you could try something like product quantization. Product quantization is slightly more complicated than binary quantization because it takes the vector, it cuts it up, and then it says, okay, I'm going to cluster this segment of all of my vectors together, and I'm going to find some centroid that represents this. And then it does this for every single segment. And now anytime a new vector comes in, you take the first segment and you say, okay, instead of representing it with these numbers, I'm just going to assign it to the ID of the cluster that I use for this segment. And I've got so many segments, so now I only need to remember what those cluster IDs are, and that's all. Initially, we started with product quantization, then we went to binary quantization. Now we're also looking at a couple of other quantization techniques. Scalar quantization is another one where you simply take the 32-bit vector and you reduce it down to 8 bits. So there's a lot of different things that people are trying out. But the reason why this reduces cost, the reason why I said people are not using it as much as they should is that it's almost like a superpower, right? You start to think that using vector databases will cost you thousands of dollars, and then you apply quantization, and not only does it cut down the memory cost, but you can also run, depending on how many objects you have, you can run brute force search, right? If you've got 10,000 objects or 50,000 objects, you use binary quantization, you can run in-memory search. You don't need to build approximate nearest neighbors indexes or anything like that. So this is another feature that we implemented where given a certain number of objects, you can just vectorize them, then we binary quantize them, and then we call it flat indexing, where we don't even build up the HNSW graph. We just do brute force comparisons. And because the binary vectors, you can optimize the distance comparison between them. It's quite efficient, and you can get away with just brute force searching through them up to a certain number of objects.
I think quantization, it builds on the assumption that there is still noise in the embeddings. And if I'm looking, it's pretty similar as well to the thought of Matryoshka embeddings, that I can reduce the dimensionality. What do you think? Like, what technique has more potential for the future, quantization or Matryoshka
Yeah,
embedding?
I would say that Matryoshka embeddings are kind of like a type of quantization as well. So this is an interesting question because in the case of Matryoshka embeddings, what people are doing are basically changing the loss function so that the learned vectors, the distribution of information in the learned vectors is not all the same. So when you use a off-the-shelf embedding model, you can't really say, okay, dimension 57 is really important, so make sure you never quantize that, right? Pretty much every dimension is equally important. And when you look at the variance of numbers in the dimensions, they're all pretty much the same, which is evidence towards the fact that, oh, all the dimensions are capturing an equal amount of information. And when you apply binary quantization or PQ on top of those, you take that into account. You don't squish one dimension more than the other dimension because they're all equal. MRL, Matryoshka representation learning, changes this, right? It says the first X dimensions are much more important, the two N dimensions are less important, and then you keep on going. So by the time you get to the end, the dimensions are not that important. So it's almost like saying the first 100, 500 dimensions will give you all the information you need, and then the next 500 will give you a little bit of details around those main dimensions. I think this is quite a unique way. I spoke to the first author of that paper, and he said that the motivation behind that paper was that he didn't have enough compute when he was running experiments. So he wanted to train four models. So he nested the loss function for those four models together, and out came these MRL vectors, right? Where you've got the first 500, the next 1000, the 1500, and they're because you've nested the loss, you've got like different amounts of information being captured by every dimension. And it's interesting now that this technique is being used so widely. But in going back to your original question of which one I think is more promising, I think probably normal binary quantization and things like this because it doesn't require the initial embedding to be trained in any particular way. I can just go in and apply PQ or I can go in and apply BQ and it will be okay. Now, Having said that, Cohere did some work and their new embedding models are quantization aware. Their loss function has binary quantization and they also have scalar quantization into account. And they prove that if you train the embedding models to know about quantization, you can actually keep a lot more of the accuracy. So this is going more towards what MRL was doing. They're letting the embedding models know to optimize through changing the loss function. But yeah, a lot of people right now are just using these PQ, BQ techniques without the loss function even knowing about it. And this is why I think it's a little bit more doable, where in Weaviate, you can put your data in and you can say, okay, just enable BQ or enable PQ. If the embedding model was trained with the quantization technique in mind, you'll lose less recall. But for MRL, there's no way you can just enable MRL. If I have a vector here that has no idea of MRL, I can't just say, now it's MRL. You kind of have to fine tune the model with an MRL loss function to turn those vectors into Matryoshka vectors, which I think is a bigger barrier for people to use MRL as opposed to just saying configure a vector database to use BQ or PQ. That I think is a lot more easier. If OpenAI is now providing MRL vectors, that of course you don't have to worry about it then, and you can just start chunking it. I think a lot of people are using those and they're discovering the power of that. The other cool thing that you mentioned before this was the multi-vector support. I'm really interested by this idea of how MRL can take advantage of multi-vector support to do adaptive retrieval. That's another really fascinating thing that's happening in the field where people are doing search on like smaller vectors that capture more information. And then if you want to get more accuracy, you take a bigger piece of the vector and you redo the search. Take an even bigger piece and you redo the search, depending on how much time you have, depending on how much time you're willing to invest for that query versus how much accuracy you actually want out of that query as well. So I think that's another really interesting topic that is unexplored right now, but a lot of people are moving towards.
And especially looking at embeddings, I think I still sometimes it's like the vector store. I'm still sometimes torn between like a feature store and a document store. Like, how do I transfer each of those models onto a vector database? How would you place like a vector database in the general database sphere, and how does it delineate from feature stores, and how does it delineate from document stores?
So I would say a vector database. This is something that we were initially in the company talking about, like a vector search engine versus a vector database, and then an AI native vector database. If you think about an AI native vector database, essentially what we mean is you've got the database kind of core component, but all of the AI related stuff, like the inference, the embedding model that's required to generate the vectors, also is connected to the database. The quantization models are also connected to the database. The language model that you might eventually be using to generate off of what you retrieve can also be easily hooked in and integrated into the database. So if you think about this idea of an AI native vector database, this is what we mean by it. Everything that you need to build the AI app should have an easy integration into the database or should live in the database itself or be connected to the database. If you think about it from that perspective, I think this is kind of a core infrastructure that is touching all of the other parts of your AI native tech stack. Whereas a feature store, I think, is probably a long-term store for your vector embeddings. If you have a data engineering pipeline and you're taking those features and you don't really want to perform vector search over them, right? If you store it in a vector database, then you're going to be paying for that. There are ways to get around that, but you don't just want to use a vector database to store your data and never search over it, right? That's what a feature store is for. If you want to take your data and then you index it, you store in a vector database and you're performing a large number of queries and you're actively using that data, actively updating that data, modifying it as users are interacting with your platform and changing the representations, that's what I think a vector database is useful for.
Yeah. Are there any plans to actually support like pruning of the database, like removing unused vectors, or even integrating something like foreign data wrappers that I can hook into a cloud storage where like older embedding vectors are stored?
So this is something that we're actually changing now. But when you delete a vector, because a vector database is, it has all the capabilities of a normal database, you can do all of your CRUD operations. When you delete a vector, If you have an HNSW index, it's not as easy as just kind of disappearing that vector because that vector is connected to a bunch of it's a proximity graph. So it's connected to a lot of the data points in the proximity of that vector. So getting rid of this vector means that you have to update the dependencies, this node on all of these other nodes. So you have to either connect them to each other because now this guy is gone. So that algorithm is already in place. So when you delete a vector, that removing that from the graph is already there. I'm not sure what you mean by pruning. Is that what you meant,
Yeah,
or
basically
did you mean
removing the nodes.
exactly? So that's always been there. That's like a core functionality of vector databases. We are updating it and making it more efficient now. Before we used to just reconnect. This way, let's say you had three nodes, 1, 2, and 3. If you wanted to delete this guy, we would just take the connection from this guy and this guy, and we would connect them. And now, because there's no connections here, there's no way for you to, as you're kind of spider webbing, jumping from node to node, there's no way for you to go from this node to this node. There's only a connection between this node and this node. So now this guy might as well not exist. It's still there physically, but it's not accessible. And then when we have some downtime, we would just remove all those unreferenced nodes. But now we're actually making that algorithm a lot more efficient.
Nice. And what is really interesting to me, like the focus on recall, especially versus precision. What are actually the levers I could pull in a vector database to also bring precision into the picture beyond like the similarity threshold?
It depends on your application. So we've talked about the HNSW index. You can modify the parameters of the HNSW index, and that will give you some control over precision. Outside of that, there's a lot of other things that people are doing now. And this is because of the popularity of RAG. People are realizing that the R part is just as important, if not more important, than the generation part of their RAG stack. Because if your R part sucks, then the generation will be full of hallucinations. So people are coming up with all these techniques to do retrieval. Initially, the conversation was mainly around chunking. And then people realized, like, what if we have huge documents and there really isn't a good way to do semantic level chunking over those? How do we capture those? And then people realize, okay, you have to use classical keyword search in those cases. If you have gigantic kind of textbooks, there really is no way to do single vector. You have to either do multi-vector support or you have to fall back onto things like BM25 where you're doing keyword searches through those. And then people said, okay, let's say we combine vector search with keyword search, we can use hybrid search. And hybrid search gives you really good improvements in recall. So pretty much all of the use cases that we're seeing take advantage of hybrid search because you have this kind of fine tuning parameter to say how much vector search do you want and how much keyword search do you want. I think that's probably the biggest boost. Another boost is using re-ranking. A lot of these models in vector search, they're relative in the sense that the distances you measure, like in one model, a cosine similarity of zero point 0.9 might be considered very high, but in another model, if you use a different embedding model that was trained differently, a cosine similarity of zero point 0.6 might be considered super high. And then if you're looking at dot products, in that case, there is no bound. So then the threshold of similarity depends entirely on the distribution of your data. So you have to kind of see the average distance between vectors and you say, okay, anything above this or below this will be considered similar. So I think using these more powerful models like re-ranking models, you can really use that to increase precision as well. So this is another thing that we've recently been adding to in Weaviate. Because we want all of these different tools to be accessible from the user of the database, we've been adding modules that allow you to say, do hybrid search, but not only do hybrid search, but now that you've gotten like 25 things back that are relevant, do a re-ranking on these 25 things. Right? So you can call a re-ranking call on top of the hybrid search call, and that's going to go through your 25 objects, and then it's going to compute individual scores of the query and all of these one by one, and then it's going to re-rank those for you. So I think that's another cheat code that a lot of people are not using. And it's a very simple add-on to your current workflow. Instead of just doing vector search, you can just do vector search with re-ranking and you see an immediate boost.
Do you already support that I can search with a different vector, like in a multi-vector system, that I can search with a different vector in another vector? If I, for example, have two vectors in a multi-vector system, like one for the entire document and one for a summary, can I use the summary vector to search in the entire document vector store or in the vectors?
Before I answer the question, the assumption is that the machine learning model that's used to generate the entire summary vector and a chunk of that are exactly the same. So currently, we just added a multi-vector support. I'm not too sure whether it's possible to search. Oh, actually, you can. So now that I'm thinking about it, so let's say you configure the database. You start up Weaviate, you configure it. You want two named vectors. You've got the summary vectors and you've got chunks from the original document. You've got those two indices. Now it's going to go in and build up an HNSW graph of summary and one of chunks that you've extracted from the document. And now let's say you come in with a summary. If you go in with the summary and you go to the first named vector, the summary index, you'll get back other summaries. But if you take that summary, you vectorize it with the same module, because these two indices are vectorized using the same embedding model, you can just take the summary and search the chunk index over this. And this allows you to do summary to chunk search. And if you do the other way, if you have chunks and you want to say, okay, what summary might this chunk have come from? You just take the chunk, pass it in as a query to this first named vector, and you'll get back summaries. Initially, I was confused because I wasn't sure whether that was a database level thing. I think on the database, the only thing that you need to have is multi-vector support. The query itself can be rerouted to one named vector or the other, and that would handle that.
Yeah, and this opens like way more recommendation system use cases, but also really fun rack use cases like the adaptive one you mentioned before that you actually can escalate to like different presentation. Nice. How do you actually see vector databases changing the way we actually store and process and interact with data over the next like 3 to 5 years, like horizontally?
Vector databases are pretty much the commercialization and the productization of representation learning. Initially, when I started at Weaviate, I didn't know what vector databases were. And then I started learning and I realized that vector databases are just representation learning scaled up and made available, where any company can use representation learning to do search and retrieval. And so this is super powerful because machine learning models in PyTorch or from papers are very inaccessible to a startup or even companies that don't have machine learning experience. And where I feel vector databases come in kind of and save the day is that they abstract away all of these different things. You can make smart default choices about the HNSW index parameters, what type of index you want to build, what machine learning model you want to use initially. Like you can just go ahead with a default one and see how well it works. Of course, getting your feet wet, fine tuning the embedding model, and doing all of this stuff will improve the accuracy. But when you want to go from 0 to 1, someone not using vector search to using vector search, I think the way vector databases will change the landscape is that people right now, when they want to search, they think in a very computer manner about how the search needs to happen. We look for words or we look for matching patterns or something like this. Vector databases allow you to take all of the advances that are happening in machine learning and now just simply turn a switch and use them for your application. I think this is a really exciting thing. That you mentioned recommendation systems. I can go from searching for recommendations over product descriptions to now combining that in a multi-vector world with searching for recommendations over the images and how those products look. I don't need to be a machine learning expert to do that now. In fact, we have an entire kind of section of our team that are working on educating JavaScript developers and web developers on how to use vector databases. Can you imagine? You don't need to have any machine learning expertise to use it, right? You don't even need to learn Python now to access all this machine learning knowledge. And I think this is really the power of vector databases, right? I think it lives outside the machine learning world where everybody can now access really smart human level search for their applications. And so in 5 years, I have no idea where the field is going, but in the next year, 2 years, seeing people take in vector search and use it for their web apps, I think that's gonna be very revolutionary.
What are maybe some of the most interesting but also like weirdest use cases you've seen implemented on top of Weaviate?
There is one particular application where this person I spoke with was looking at different palm images and they were trying to see if they could, because palmistry is an art and people are really interested in it, they were trying to embed images of people's palms and they were trying to see if they could, given your palm, situate your palm and find out other people's palms and see if they could find some sort of, if they zoom out, see some mosaic of, oh, these palms end up rich, or these palms end up living a long life. This was like, if you're asking about the weirdest thing, this is, I think, probably the most interesting and weirdest application. And it goes back to kind of discovering high level distributions, like semantics and data, where people think that there's something there, but let's embed it and let's see if there is actually some structure in how the way our palms look. So I think that was probably an exciting application.
What would be a use case you would love to see implemented on top of VV8?
I think there's a lot of potential with recommender systems. Like, a lot of people are going in really heavily into RAG, and it's understandable. Like, it's a very exciting space, but I think recommender systems can definitely be revolutionized by this as well. Because if you combine recommender systems with multimodality, I think that completely changes how recommendations can be made, right? Like, if you think about how recommendations are made right now, typically you're looking at product descriptions and how they interact with products that you've bought or interacted with. So if the description is similar, then you'll be recommended those things. Tomorrow, what might happen, and some companies are already doing this, that they've published Meta with their Facebook marketplace, and Amazon has already published on this, where they're doing multimodal recommender systems where they generate vectors which are combinations of images and descriptions, text and images, and then they tune these models, and then they make recommendations based on not just how a product is described, but also the way the product looks. And this allows you to recommend within a category much more accurately. So right now, if you search on Amazon or Facebook Marketplace for a couch and a very specific description, you might get other couches, but that ones that don't look the same. But if you now have image as a modality to recommend off of, now you can differentiate between different types of couches, because the description might be the same, but the way they look might be different. And so now you can more accurately identify what a user likes and they don't like, because now you have another sense. You have this sense of sight to do that with. And now if you extrapolate that into the future, there's a company that spun out of Google called Osmo that's working on digitizing smell as well, right? So now, let's say this is not publicly available right now, but they've published some papers on this. If you can embed smell, you can already embed video. If you can take all of these modalities, and a lot of these companies already have their products in these modalities, their marketing teams know what a Coke sounds like when you pour it, or what a burger sounds like when somebody eats it, because those marketing assets are already there that they're using in their advertisements. Now, maybe like 2, 3 years into the future, you could search and say, this is the perfect burger. This is the crunchiness of the burger. This is the perfect perfume because I know it smells exactly like this old memory from my childhood or something like that, right? So now you've got recommendations on those other sensory inputs, which is impossible to imagine right now. I think that's what vector search can enable in a field. There's some companies that we're talking to and working with right now that are taking advantage of this multimodal recommender system stuff. I think that will only improve. And I think 3, 4 years from now, we'll be amazed by the recommendations and what senses they're coming from. I think that is really going to be powerful.
Yeah, and especially in recommendation system, you can even extend it to the user side as well. So one use case we are exploring at the moment is for basically skincare, where you have images of the user conditions. You have the images of the creams of the products. You have the description of the products. You have the ingredients. You have the description of the condition of the user and also the description of the user. And through that, you can do like so many different interesting things. Like, what are you now like basically matching on, and but also like the reverse, like if I can't find anything that matches, this already points me like there might be an interesting anomaly, and I might even hint it like you should go to a doctor and actually talk to them.
For sure. One other interesting thing that I was thinking about for this is a lot of these big corporations, they want to know consumer buying patterns, right? If you're buying product X versus buying product Y, why did you buy X and not Y, right? If you think about this multimodal search a little bit more, and if we're thinking about which senses a person is using to buy shoes versus what senses they're using to buy a soft drink, like, this is completely academic right now, but maybe in the future, if you have data around which products were purchased and which modality was more important for that purchase, you can do some testing to say, okay, when we do soft drink recommendations based on how they look or how they sound, more people based on those recommendations tend to convert and buy, versus if we just do it based on descriptions or nutritional facts, people don't buy it. Okay, so now you can even understand which products are bought using which senses. I buy burgers because of the way they taste, not because of how they're described. But clothes, I buy because of the way they look. I don't really taste the clothes, so that sense is not useful. So I think you can kind of break down user intent across these modalities down to a science, which is also, it's kind of scary, but it's also interesting because now people are used to looking at a YouTube ad for 10 more seconds than they do on average, and all of their ads changing into that type of ad. Now you have to be wary of how you're using your other senses as well, because now if you can capture that sense and embed it into a vector, now that's potentially a way to be recommended an item, right? It's kind of scary to think
Yeah,
about.
we finally made it. The tech weeks can actually quantify psychology.
Yeah, exactly. Yeah.
What is next for Weaviate? What you already can tease a little bit.
We've got a release coming out where we're going to change how no downtime upgrades work. So we're releasing Craft. By the time this comes out, it should already be live if there aren't any big surprises. But that's a big thing. I think the multi-vector support was rolled out in the last update. People are now starting to use it. And I think the quantization support. At the beginning of this year, we had one way to quantize, and within like 4 or 5 months, we're supporting like four different quantization techniques. So we're going really heavy into making vector search affordable so that it's not even a thought, right? Going, if you want to do search, you're going to be using vector search. So we're investing a lot into that as well. I think those are the main frontiers on the vector database technology that people should look out for. The other thing that we're doing, because we're bringing everything that's AI related closer to the database, is making it really easy for people to go from 0 to 1. If you're thinking about using a vector database, or you don't need to learn how embedding models work, you don't need to learn about all of that. You should just be able to like write a few lines of code to try this thing out, build a POC, and then help them scale it. So I think that those are the main things that we're focusing on right now.
What technology are you most excited about outside of vector databases and LLMs?
Literally the only things that I think about are search and generation, like LLMs. And so my background originally is in biomedical engineering. Brain computer interfaces are a technology that I am super, super excited about. I don't know a lot about gene editing, CRISPR. If I knew more, I'd probably be more excited about that. But I think brain computer interfaces are very, very exciting. There was a paper that came out where we have language foundation models. They built a EEG foundation model. They took the signals from your brain, the electrical signals from your brain, and they trained a foundation model to understand those signals. And I think if you take software like that, if you take foundation models that can understand the electrical activations in your brain, then you combine that with hardware, whether it's non-invasive. So there's a lot of non-invasive kind of headbands that are trying to measure EEG signals. And then, of course, you have Elon's really invasive device that goes into your brain. But if you take those technologies and if you take representation learning techniques that allow you to decode brain signals, that I think is super exciting. That is kind of related to vector databases, but I think it's sufficiently different because representation learning is in everything. I don't think you can get away from that. But BCIs are super exciting to me.
Yeah, and there's like also like interesting development. There was a DeepMind paper on predicting weather with a graph structure which was overlaid over the longitude and latitude lines. And I think this was, and they also used basically an autoregressive model to predict the changes in state. And I think this is a principle you could also really interesting apply to the brain if you have like enough data to actually understand it. And this is also like a form of embedding because you're mapping onto a smaller structure, which also gives you a better feature, which you can better work with. If people want to start building the stuff we just talked about, where would you point them to?
First, you can get started. You can go to weaviate.io and you can have a look at what we're building. There's a lot of education material, there's blogs, there's the Weaviate podcast. Everything that we do at Weaviate is open source. We're even building. So if you want to get started with RAG, I would suggest people go to Verba. It's an open source GitHub project that we're building and maintaining and upgrading at Weaviate. It's probably the easiest way to go from having no RAG application to having a RAG application POC within a day. You can fork Verba and you can change a lot of the things that are modifiable. You can change the embedding model. You can point it to a GitHub repository. You can embed all of your data. It takes care of a lot of the things for you. It automatically chunks, and it's almost like a production ready app that is customizable to your data. If you're interested in that, I would get started with Verba. If you're interested in learning about multimodality, if you're interested in working with vector databases, we also put out a lot of educational content. So we've got a couple of courses on LinkedIn that you can look into that teach you about vector databases. We also partnered with Deep Learning AI to put out courses. So if you search for Weaviate Deep Learning AI courses, that will also get you started. And also, Weaviate Academy is a great resource. So if you're getting a 101 on vector databases, I would go there. And then we're always adding new courses and new material. We just added a new module on multi-vector and how to use that for recommender systems for movie recommendations. So I think those are some of the resources. And then for more interactions, if you want to reach out to me or if you want to reach out to anybody at Weaviate, you can join the Slack community, you can join the forum, and you can ask questions. We're very active there as well.